started. Last Saturday, Kevin, Blythe, Sophie, Katie, and I went to Biosphere 2 as part of our continuing kind of partnership where we can participate in their Science Saturdays event. We made liquid nitrogen ice cream and talked about life in the universe, so we would make like a comet that had an ice cream core and sprinkles and Oreos that represent the dirt, and then a whipped cream tail. So the smartest kid in our little audience got to eat the comet, and then everyone else got ice cream. So that was really successful. We actually ran out of material for the ice cream, so we just played with liquid nitrogen until we were done. Moving on to further events. Club, it's supposed to say Camp Wildcat, is a organization that promotes college for underage kids. These are, I think, elementary to high school students, and they hold a camp where they take them out and do activities and such. And at the club fair and recently by email, we were contacted them because they're having a space-themed camp March 4th through the 6th, and they wanted us to come help them. Unfortunately, March the 5th is the first Saturday of the month, so we have our Sabino Canyon thing. But I told them we might still be able to help. We could do something Saturday or Sunday during the day. We can like look at the sun or Venus and talk about different astronomy stuff, and we can do something Friday night. So that's something that's probably going to happen, and keep listening for more information about that. Before I get to the rest of the presentation, we're planning on having like a club social event around this time, or early March. And we were just thinking about ideas of bowling or having a movie, or I don't know, hide and go seek in Stewart, or go fish. So do any of those ideas appeal to you? Any hide and go seek? Anybody else input? You second that? Okay. I'll move that information along. Now just talk about some standard stuff. We have lots of projects going on, as most of you know. Extrasolar Planet project, we're finally really getting to reducing our data, and we will hopefully have good data soon. Right, Jake? Yeah. Yes. And we meet Thursdays at 6:30 p.m. in the computer room directly below us. The Monocular Telescope project, we recently received news that we are probably going to get mirrors from Celestron at
significantly less than $700.
Significantly. Yeah. I mean, more than 1%, less than 20%. That's what I assume when I hear significantly less. And that's great, because we were kind of stuck on our mirrors before, when our contact was not being very polite and did not tell us about their problems. So that's going to really start picking up soon. And also, every Friday at 3 p.m., we during Katie's office hours, we talk about different outreach materials. Like, if you want to talk about cool ideas like liquid nitrogen ice cream comets, or I don't know, our planet model, and it's really fun, and we don't have a whole lot of people going there, so it would be really great for you guys to help out. And speaking of the outreach, I just want to make a note. I did a presentation on the Hubble Space Telescope for my classes earlier, and one of the points that got brought up is you all know of the Hubble Space Telescope as the great amazing observatory that we know of it today. But initially there was a slight problem with the mirror, and so the images weren't as good as they were promised to be, and so that really got a bad public opinion for the Hubble Space Telescope and astronomy in general. And so NASA and Hubble specifically really got into this outreach idea, and so that's how we're getting continuing support for Hubble and stuff like that. So it's really important that the public knows the awesomeness that we do.
In the early 90s, when they were talking shutting down Hubble, the biggest cries to keep it running again were actually from the public, not from scientists, because they saw these images was coming and people got
Yeah, and I forgot to mention we got $42 at Biosphere, so people are pretty impressed with what we do. Just another event, astronomy question of the week. If you like just talking about astronomy outside of class, you don't have to do lots of math or just kind of fun stuff, this is a great place to come. It's run by Don McCarthy, who's, if you know, is a really great guy. Yeah. If you checked your email this morning and you're on the steward listserv, hopefully you got my spam to all stewards saying if you want to give a talk about your research, we're definitely welcome for you to, because we're interested in learning about everything that people are doing. Dues are, just mention unless dues are $10 a semester, and it helps support all these cool projects that we have. And if you sign a membership form, it's online. It really helps us. Yeah, I found it. This picture I found on the website. We just have this, and this, I think, was from a star party a couple of years ago. And so now we have a presentation by our own Jake Turner about his research on Titan.
Okay, so I've been doing research on Titan. Whoa! So he's gonna knock me dead. For the past year, pretty much, almost straight. This is my research I did during summer as well. 30 hours a week, so it was a lot of research essentially. So, as you guys all know, so just a brief overview of what I'm going to talk about. So this Huygens Cassini probe is what I use all the data from. The characteristics of Titan, what makes it so interesting to study. The tool that I use is a program called Titan Browse and something called Radio Transfer. People in this class a lot about, which is why I did it. And then some of the stuff I helped discover in refining, such as the methane clouds, the tropical lakes, and the tropical surface orbiter. So this stuff I'll talk about. So Cassini was launched in 1997, and it arrived in 2005. It has currently 12 instruments on it. 3 of the instruments that I've used in my research is what's called the ISS, the Imaging Space Subsystem, the radar, and then this one I use the most called VIMS, Visible Instruments Mapping. And obviously it's designed to study Saturn and its moons, but also when it was trying to get gravity assists in the solar system, it passed by Venus and got spectra of Venus. It also passed by Jupiter and got some really good data of Jupiter as well. So, and it also took pictures of spectra of the moon and Earth, and so it was actually what its main thing is. So the Huygens probe, I didn't say how many instruments it had on it, but it had about 7, 8 instruments on Huygens probe. I remember. And I think everyone's seen this picture before. It's one of the most famous pictures from Huygens probe. And so it descended through the atmosphere, and as it was going through the atmosphere, it measured every characteristic known to man, essentially, trying to just figure out what it was made of, how it behaved, stuff like that. It's very interesting. And it's also the only direct surface composition measurement we have. And all these rock pebble things that you see are solid water ice, essentially. Because it's really cold on Titan. And one important point that I'll mention, and then I'll get back to this, is during its ascent, it lost one of its communication channels, and so it lost some of its images. But everything else, all the other data that it had, it survived. But some of the images that it was taking along the way were lost. And so, just a few facts about Titan. It's the second largest moon in the solar system. It's actually bigger than Mercury itself. So, for comparison on that. It's also the only moon to have a fully dense atmosphere. As you guys can see, there's a very thick atmosphere. It's about 10 times thicker than Earth's, put in comparison. And also on Titan, there is something called a methane cycle, where methane can be a solid gas or liquid on Titan. So it's essentially the same thing that happens on Earth with water, except it's on Titan it's with methane. So there's lakes, there's rivers, it rains, it snows, all the wonderful stuff that you guys happen on Earth. So just a little bit more about the atmosphere and why it's so interesting. So it's very opaque. So some of those images I showed you, you can't actually see the surface, like this one in the background. So only at certain atmospheric windows can you actually see the surface. And with the VIMS instrument, you can only see it at 6 distinct atmospheric windows. It's made of mostly nitrogen, kind of like our atmosphere as well. There's some methane, which 1.4 lot, but it does a lot of stuff on it. And then there's hydrogen, and then just some trace hydrocarbons. And why they believe Titan looks the way it does in the visual anyway, with this like orangey thing, is these things called tholins. This is a certain type of organic molecule. And one of the most interesting things that they've been able to find so far is experiments done in LPL, which I haven't been involved in this, but why everyone just loves Titan so much is because they found that they're able to make nuclein bases, which are basically base of DNA and RNA, which Katie could probably tell you guys a lot more about that. And also amino acids as well. And it's the only other place in the solar system that we know this can happen, essentially. So there's like people that say there could be like, if you get really underneath the surface, because there's a tidal effect from Saturn the same way there is on Euclid and Enceladus, where it like spews out stuff. So they believe the same effect happens. So like if you go down in the core of Titan, essentially it's really warm, so like all that water ice on the surface can melt and become liquid, and then it could be subsurface life essentially. So this is actually, if there's a way to detect that, which there could be, it's a great place to even detect life like Earth's. And if life can be developed on methane cycle instead of water, then maybe that too. But that's a whole different thing. So more about the instrument that I use. So this is 3 different wavelengths that you can see. This one is in the visual, this one is infrared, and that's also infrared. So you can see just the different ones that you can't see the surface, you can see different surface features essentially. So essentially what VIMS is a spectrograph, but it takes images from 352 different wavelengths. And so essentially when you get an image from the instrument, it looks like this. But each of these pixels is a spectrum, essentially. So you can look at each of those pixels, and it's a spectra from all of them. So essentially, it's kind of like double duty, essentially, in that sense. And so the ones that I'm going to be talking about today are at these atmospheric windows. So they're really important. And there currently is over 11 million spectra that VIMS has taken of Titan. This doesn't include the other moons and of Saturn and the rings and stuff like that. So this instrument has a lot of data out there, essentially. And that's of 2008, but there's been several passes since then. And so with 11 million spectra, how many people want to go through that by hand? You want to go through that by hand? It'll take you the rest of your life. And so the one, so that's essentially, we got all this data, and we were like, how do we search for stuff that we want to search for? Like how do we find clouds or lakes or anything in general that we want to study? So there was this program called Titan Browse that was created in order to do this task. It was created by a student in LPL. He was a grad student, and this was actually his thesis. And he created it in order to rigorously search the Cassini data. So if you're like, I want to look at data just from this pass, so this day, you can do that. If you wanted to look at data from certain lighting angles, which is really important, then you can search all the data that has that exact lighting angle. And then you can also search stuff on the surface as well, like is it this bright, is it that, and stuff like that. So it's very rigorous. If you're like, I want this spectral feature, show me all the data that has it, you can find that. It's powerful. It's a really powerful tool. So if you are trying to look at clouds, they have a certain spectral feature, so you're like, I want to go look at these. And I learned how to use this pretty much all last fall semester. It's pretty hard to use, but once you realize how to use it, it's like extremely powerful. My professor doesn't even know how to use it, for that in sense, so she's like always asking me, she's like, hey, can you search this thing for me for another project she's working on? Her husband asked me to use it before as well. So yeah, it's pretty powerful. But when there's problems, it's really hard when there's problems because like not very many people know how to use this. And the person who developed this is now, as I say here, and why there's actually random ass pictures of jungles, is he's currently in Brazil in the jungle doing I don't really know what. But he's the hardest person to get in contact with ever. So if there's ever a problem, I'm like, oh gosh, how do I get in contact with this guy? Like, where is he at? Like, it's ridiculous. So the one person who knows the most about this is the hardest person to get in contact with. Which I think I mentioned this to several people. I'm like, I don't know how this program is working. Like, I need to contact this guy, and he's like in the middle of the forest in Brazil. So these are the only equations I have on my slide. But so I was talking about the rate of transfer. So essentially what rate of transfer is how light is scattered through the atmosphere. Sounds pretty simple, right? No, it's not. So essentially, this is the equation that we are trying to solve in order to figure that out. And there's lots of techniques in order to solve this equation, and it's just a lot of work, and there's a lot of derivations and stuff. And so one of the techniques that we use is called the tree-oriented rate of transfer, and it's one of the most fastest, most like realistic approach, essentially. Most people don't do this approach because you have to really know what you're doing in order to do it, essentially. And my professor's been working on this for the past like 60 years, 50 years. So she's been working on it for a long time. This was actually her thesis, and she kept on doing it and stuff like that. So essentially what you do is you divide the, this is the layman's term way you do this. Essentially you divide the atmosphere into different parts. In our code we do about 72, depending on how we feel on that day. And then for each of those 72 layers, we use the effective optical depth, the single scattering albedo, phase function, and astronomy parameter. Do you have any idea what those are? Does anybody have any want to say tell me what those are?
You tell me.
I'm asking you. Can you tell me anything that I just said?
Albedo is the amount of light radiated from a planet, thinking of what it received from the sun.
It's true, but not in this case. So one thing I was like looking for papers. I think I told you some of this about the albedo Titan, and there's a difference between single scattering albedo and just albedo in itself. So single scattering albedo is how the molecules themselves behave when light is on top. So it's kind of the same thing, but not really. And so all these parameters that we use for this were obtained by the Huygens probe. So that's where that comes from. And so we're using real data that went through the atmosphere, measured at each of these layers, and so that's actually how we know to divide it into 72 layers, because within an Orion magnitude, that layer is pretty much constant with all those parameters. And so phase functions are really hard to deal with. They're horrible, and one of the ways we do it, we use what is called the Lagrangian polynomial expansion coefficients, which I think Kevin's worked with that before.
Quantum mechanics.
Yeah. So it's all quantum mechanics. It's horrible. It's ridiculous. subject. But and so this is used for like I said, realistic things, inhomogeneous, non-isothermal, and it basically predicts how much light is bounced up and down and sideways through each layer. Can do any direction, so in a sphere, any direction, any position in the atmosphere, essentially, that you want. So it's pretty awesome. And also we use what is called, we use 32 streams, where other people's models use like 2. So what this means is, as light is bouncing off of the particles, it can bounce either up or down if you use 2 streams, or 32, it can bounce 32 different radial directions. So obviously that's more realistic, but you should use more than that to make it but this code takes longer. And so then the solution that we get out from this wonderful code is that. Isn't that awesome? I can read that.
That's simple.
It's pretty simple. You should see what that looks like. Pretty ugly. But so depending on what parameters we put on this and stuff, this code can take up to 15 minutes to about 2 days to run. So it depends how realistic you want to get, what your parameters are. So sometimes we only run certain parts of the spectrum, like from 2 microns to 3 microns, so it takes shorter time. But if you go from 1 micron all the way to 5, then it takes longer, and it just depends on what you want to do. We can also add clouds to this. As I will be talking about a little later, we can add lakes to this, see what effect the lake has on the spectra, which is actually one thing that, so this code has been developing over the years, and so while I've been working with it, it's actually been evolving at the same time. And so the one thing that we added recently is a lake feature, actually. You can put that into the code and see how it behaves if there's a lake on the surface instead of just surface stuff. So yeah, it was like a few days, me and my professor went over this code. It's like 2,000 lines long itself, but then it has like 50 subroutines, and each of those subroutines are thousands of lines long, and it's ridiculous. So the first part of this research I started with the clouds, and I went to talk to my professor and was like, hey, you have research I could do? She was like, yeah, you can study the clouds in Titan. And I was like, okay. And so she was basically just use that program called Titan Browse and look for clouds in the northern hemisphere, and then eventually that went to the tropics as well. And that's essentially what I was doing. I was looking for clouds, and they're pretty easy to find on Earth, obviously, but not so easy on Titan. So essentially from our radio transfer code on these clouds, we can determine their density and their height. And how that actually helps anything is from the height you can actually infer stuff about the surface, like the surface humidity, which is really good. So if you wanted to know if it's going to rain on Titan, let you know the surface humidity, essentially. So that helps with that. So yeah, and so with Titan Browse we can also determine the frequency. Like I said, it searches all the database. And frequency distribution, like where they are there certain spots on the planet, are they in different spots and stuff like that. So these are some of the clouds. I don't know if these are clear or not, but these are some of the clouds I helped discover. As you can see, they're varying in resolution. So you can see the whole disk here, and you can see that wonderful cloud right there. So that's a methane cloud. And then I don't know if you can see in this picture or not, but there's like this kind of little haze thing right there. You guys see that? Yeah. That's an HCN cloud, essentially. It's always in that one spot on the planet. So it's kind of weird. And then this is also another big storm on the bottom here as well. And then zooming in a little bit, you can see streaks of the clouds. And then there's another smaller zoomed in cloud. Yeah.
What is HCN?
Oh gosh. Is that how you know? So it's kind of weird because it's like very ambiguous. And so we model these clouds and we're like, okay, what can we find? So essentially what this is showing is the difference between the cloud. So you can see the cloud and not cloud surface are a little different. You can see that they're not the same brightness and stuff like that. So essentially what we do is we find a pixel on the cloud and we find a pixel off the cloud. We subtract them and it should give us the parameters of the cloud essentially in that sense. And so that's basically what I did for this one. And as you can see, so these regions right here on the graph it's supposed to be straight. That's not the and so those you can't actually see the surface on that, so it kind of makes sense that they're straight. And so these are 3 of the atmospheric windows that I was talking about, where you can actually do this. And in this region right here at 1.6 microns is the most susceptible to the height of the clouds. And so you can see I have 3 different models here at different heights. And so this height is 26.5 kilometers. So, but then there could be lower clouds as well. And so this is the same thing before. You can still see these are flat, a little flatter than the last one. And this one is at 14.4. So we've actually been able to determine clouds, different heights. So that means the surface is not just the surface humidity and temperature and stuff like that. It's not all. So as I was doing this research this summer on the clouds, something happened. We were talking about. So lakes, there's lakes on Titan, like I told you. But what's interesting about Titan with its lakes distribution versus Earth is all the lakes are on the south and north poles. So here's the south and north pole, and all these shaded in red areas are where all the lakes are discovered so far. So there's some little small ones, some big ones, and so these were all discovered with radar, essentially. And so this is one of them down here from the radar. You can see interesting kind of structure. I think they made, this is a false color, obviously, and so they made it blue, but probably because lakes are blue on Earth. I don't know. But, and so, yeah, they're only discovered in the north and the south, and they know that they're made of methane. But then there was one study that hinted that they could be made of methane as well, which I will talk about a little bit.
Do they know that they don't exist anywhere else besides like the polar plate?
They've only been able to confirm that they exist at the poles.
So they're just not really sure about the
I'll be talking about that next.
What would be the true color?
No idea.
Yeah.
I have no idea what the true color would be. So like, as I was saying with the model, you have to say what the atmosphere does. And so you have to model what all the atmosphere light bounces off, and then how that goes to the lake, and how that bounces back, and then it has to go through the thing. And it's a little complicated. Well, they think that's from Tholins, so that's not even the same molecule essentially. So I have no idea. If you can figure that out, let me know. Yeah. So, anybody notice anything about this picture?
There's some light spots and some dark spots.
Yeah. So there's these light spots. This spot here. So as I was doing my models with the clouds, one of the models wasn't working, and I was like, "Why is this not working? Like WTF? Like what is going on? Like this should be working." And so I asked my professor, and she's like, "I don't know. Go figure it out yourself." And so she was like, "Go find one of the spectra right by the Huygens landing site, because obviously we're using all the data from the Huygens landing site. So our model of the atmosphere should be exactly what they got." Makes sense. So I was like, okay, I'm gonna go find a random cube. These are called cubes, by the way. A random image, essentially, and model. So I bring up this picture out of 11 million spectra, essentially, and this one comes up, and I'm just like, oh, there's nothing interesting in this picture. And then my professor, I was about to like exit out of it, and my professor looked over and she's like, "Stop! Just stop everything!" And I was like, "Whoa, okay." And so the reason she was so excited is because she thought this might be a methane leak. So we're like, okay, cool. What is interesting about this is actually on the equator. And so from the words of my professor, by accident, we discovered we had a well-prepared and fortunate accident. Because we had, from her point of view, we had all this machinery, like the code and all that stuff. We had the Huygens data and all this stuff that we can accurately determine what the atmosphere is doing, so we can accurately determine what the surface itself is doing. And so the first thing I did was try to look to see if this only appeared in this image, which it didn't, which was good. That was the beauty of the code, the Titan browse. Like, if we found this one image and I'm going to go try to find all the other ones from the passes, like, it's going to be very hard. So luckily we had that, and it was a lot easier, per se. And so this is what happens when we use our code, run it through the atmosphere, and get out essentially what is called the surface albedo, which is what Black first mentioned, is how bright the surface is itself. And if you use bright region again, and this varies by how bright and how dark they are. And then there are like completely black, essentially, with an error bar. So here's another cube I found. So there's our leg again, still black, which is good. But you can see this is another different orientation, different like resolution, like everything from the last one, as you can see. So it's taken at a different time, different path. And so there, right there, in that region, is where the Huygens probe landed. And so there's our leg. So you remember me telling you something interesting about the Huygens probe? What did I tell you? People listening. It's missing some of its images. So it's believed, my professor, Huygens probe, moved this direction, taking some images of this region, and they lost it. Aliens. Yes. Aliens. I should have got another plot, but same thing happened with the radar as well. The radar people have awesome resolution, as you can probably see from the last slide. They had like a path that went all the way down here, one that went over here, one that went over here, and one that went on top as well. But they missed it again.
And also some instruments that your images that close to landing site?
So no, this image was taken specifically to characterize the landing site, essentially. This is one of the specific ones they tried to look at for that. Well, when people looked at this, they were like, oh, I'm only going to care about this little region. Whatever else is there, who cares? When they got the image, essentially. So that was one of the design ones.
Do you know, like, how, the length of this?
Oh, I will tell you about that.
Okay.
So this, I'll just tell you right now. This is approximately 150 kilometers. And the resolution in that way and that way aren't the same, just the way the images work. So that is approximately 150 kilometers as well. They're not always the same resolution, upwards and downwards. I really haven't understood that, but that's what they tell me. So, yeah, in science you just never know what you're going to find. And so, just to wrap up the story with the clouds. So the only thing that was wrong with our cloud models is we forgot to multiply by pi, essentially. But if it was important, but like it wasn't anything wrong with our code. It was just wrong with the data, because some people like Cassini argued about what units to put the data in, and half of them were like, we should put it in this unit, and the other half should be in this unit times pi. Don't ask me why it matters. And so we thought we had the data that was already multiplied by pi, but we had the one that wasn't. When we figured that out, the models that I showed you earlier happened. But we kind of forgot about the clouds after we discovered this, and we were like, this is really important. So you may be asking, how do we know it's a lake? Good question, right? So one thing awesome about spectra is each element in any phase, which is key to this point, has a very distinct characteristic, has a thumbprint. So liquid methane of at least a meter deep is very important, because if it was less, then it would be different. Is the only known substance that has a surface albedo that is completely black at all the wavelengths that we're looking at. So that's the only thing that it can be. And so we used our radiant transfer model and to find the surface albedo, confirm that it was black, and within errors, it was completely black in every wavelength. And so this is another way to show it besides our model and besides the spectra. Whatever spectra is wrong or something. So this is basically albedo versus how many pixels has that albedo. So on this side it tells off, pretty like it's supposed to, essentially. If it's random noise, it's not going to go completely off. But this side, you're done. So that also helps us with the lake argument, because if it was random noise, for example, in our instrument or something else, then this should tell off and not completely drop. Okay. So, cool, we found the lake in the equator. And I don't remember why I put that. But so we presented our findings last semester, and we found this lake. It's awesome. We confirmed it, and people got really mad at us about this. Yes, it was really like that. I was trying to find some conference where some guy was yelling, but there's not many of those. So we presented this at a conference, and my professor had a talk about this lake and said we discovered it and stuff like that. And after the talk, someone stood up. So please don't stand up after this talk, but stood up and yelled at her, literally yelled and screamed. He was like, "You're wrong. You don't know what you're doing." And I'll just describe why. So a lot of people were mad, and it's science. This thing is wrong. But so why? Why were people so mad? It's a good question. So there's these things called global simulation models that basically try to simulate the weather patterns on Titan, kind of like they do on Earth. So it rains more in one spot. There's more clouds in one spot than the other. It's always cold in Antarctica, for example, stuff like that. So we're trying to do the same thing on Titan, essentially. And so every single global simulation model that there is out there right now predicts that there shouldn't be any precipitation whatsoever on the equator, due to some efficient transportation mechanism that they. And before the summer, these simulation models were confirmed by data, but now they're not, essentially. And so this is a kind of a schematic of what I've been talking about. So the planet rotates this way. There's winds on the equator and everywhere. And then there's this cycle that goes this way, essentially, to the poles, that takes all the clouds and all the methane, everything, to the poles, and that's where it rains, and that's where all the lakes are at. So that was pretty good until summer when we discovered this lake. So you can consider that to be the lake, I guess. And so there's no way under these current models that they can say why our lake exists.
Even just one lake?
I will get back to that. So what? One lake. Who cares? Yeah, so our lake is a pretty decent sized lake. It's about 160 kilometers, 160 kilometers. It's about the same size as the other lakes in the South and North Pole as well. So it's comfortable. And since then, we've also been able to confirm 2 more lakes as well in the same vicinity. A little bit smaller, but we're there. And I can't show you pictures because we've only confirmed this in the last month or so. So it's kind of like whatever you call proprietary or something. So essentially these people on the global simulation models need to relook at their code, relook at what's happening, and come up with a new model essentially to predict it. So that's essentially why everyone's pissed off, because now they have to go back and redo all the work they were doing before. So you said something about ethane. Did I say anything about ethane? What did I say? Yeah, that's exactly what we said. So we're like, okay, cool. So let's look for ethane in our lake. And we did, and we didn't find anything. And so we're like, okay, are we doing something wrong? So we went to the lakes that they just helped discovered ethane in, which is this lake. Actually, this is a picture from their discovery paper. and tried to reproduce the results essentially, and we couldn't. And we're like, so we checked. So we emailed the people and talked to them about what we were trying to do, and they were like told us their tricks and whatnot, and we did the same thing, and still we couldn't do it. And so we believe it was introduced by their data technique, introduced artifacts that were real. And these people were out a lot nicer than the last ones, and so they're actually on the new paper with us for the new lake where we're going to publish that they haven't actually discovered it. So there are some. So next, I'm going to be talking about albedo, as like mentioned, which is essentially just trying to figure out how much brighter this is and how much darker that is, and what itself the surface is emitting. I mean, there's some more clouds down here. As you can see. So why care? Why does it matter what surface albedo Titan has? We have other things to worry about tonight. And so one of the most important things you can do with that is you can determine the surface composition. So like I said before, we're only certain that there's one surface composition, one spot where the Huygens probe landed, and it's kind of hard to figure out what exactly the surface is made of. So we use our model again that accurately models the scattering properties of the atmosphere to get rid of what the atmosphere itself is contributing to our spectrum. So this is one of the first maps that we have for this. And so it's not perfect, but you can kind of see, I'll show you the next picture, so you can kind of tell. I don't know if you can see this very well, but these dark regions, well, go back, are not filled in here, but are here. So essentially we're trying to get all these dark regions and their characteristics and model them. And so this is one of the first ones of where the model we're using predicts where all the dark regions should be. And then this one is where all the bright regions should be. Okay. So, as you can tell, right here, really bright, nothing in the dark ones, something in the bright ones. So, seems like it's kind of working, essentially. So this is just one of the models that I ran, and yet again, 3 for 3 plots essentially, and so this is the model, and this is the data, and it fits pretty well, as you can see. And so some of our preliminary results for this, we found varying surface albedos that are pretty big, 70, 80, 75, 10, essentially. And so this result varies a lot from previous published papers. And so I was talking to my professor about this. You might be wondering why I still have people yelling on the bottom. All the people yelling everywhere. Who's this, Kevin?
William Shatner.
And what is he playing?
James Tiberius Kirk.
In what episode?
I have no idea.
Shh, I thought you were.
One that he yelled at.
You
Which is most of them.
Yeah, you yell at most of them?
Most of them.
Okay. So I was talking to my professor about this, and she was like, yeah, we're going to be publishing this paper about the lake, and people are going to be pissed off at us, and then we're going to publish this paper about the surface albedo, and people are going to be even more pissed off at us in the lake paper. And I was like, how is that possible? And she's like, just wait. So hopefully I'm in grad school by then, so don't want to mind me going to grad school for that. But on this preliminary analysis, so I think I don't know if I told you, but there's also dunes on Titan as well. And so this is a radar image of the dunes. As you can see, bright, dark, bright, dark, bright, dark, or where the dunes are at. So dune, essentially. So this is dune on Earth, so it's essentially the same thing. Did you figure out what episode it was?
No.
No?
But I found a hilarious episode.
So essentially, there's the dune, which is one of these bright regions. Here's the flat thing over there. So it's kind of the same as some dunes on Earth. This is Namibia, is where this is at. So it's like a kilometer separation of the dunes, the dune of sand space. The dune of sand. Well, and so with this preliminary results of the surface albedo, we've we believe that these dunes on Titan are made of water ice, essentially. So, water ice sand, I guess is what you would call it.
Snow.
Snow, I don't know. But it's essentially the same thing as sand, but it's made of water ice instead of whatever sand's made of. Yeah. So that's one thing that we've confirmed as well. So that's pretty much all my talk. This is the first picture, one of the farthest pictures that I was able to take, Christina was able to take. And so there's Titan, Saturn. So that was pretty cool. And then there's a zoomed in view, just how far it's gone essentially. And so from this research, like, I thought I was just gonna model clouds. That's all I was gonna do, and only gonna do this first semester, but turned into a year-long research experience. But the moral from my research is, like, science is supposed to be moving forward, and if it's not moving forward, then where is it moving? You know, like, if you're not disproving stuff wrong and coming up with better models and coming up with better stuff, like, what are you doing, essentially? Because everyone's always pissed off at us, and I'm like, why is everyone so pissed off at us? We're just doing science, and we're, like, doing the models better and predicting stuff better. Like, isn't that what we're supposed to do in science? You know? So, any questions of anything I talked about? Yeah.
On your picture of the lake around the pole, there's one lake that was
This one? This was just the specific paper that this is from, and they're saying something about that lake.
And, okay, I guess another one. The albedo, I don't think I know a lot about, but since you can't see, like when you look at Titan optically, you don't see the surface, right?
Nope, you don't see
So
the
is the albedo you're talking about, like, infrared?
Essentially, yeah. Just the albedo at that wavelength. So you can't get the albedo of every wavelength, obviously, because you can't actually see the surface of the visual one. But so that's why we can only get the albedo at those 6 specific things that I was telling you about. And based off.
Is that different from, like, if you're, I don't know, people who research other moons, do they look at moons?
Usually that's what people prefer because that's what most research is done on, and how you can relate that back to Earth, like Earth has this albedo and stuff like that. But we can't because we can't actually see the surface essentially at that wavelength, so it's a lot harder. But yeah, so these are essentially where we can find the surface albedo at. And certain characteristics like water ice, if you know the surface albedo at that, then it should be a certain way, and other elements and stuff like that. So,
Going back to your picture on the lakes, it showed like one big lake. Or where the Mare and the Kraken.
here.
Did the big models predict those lakes?
Yes. The models were working really well. Like, they were doing an awesome job. But until we discovered our lake, essentially. But they were predicting what we knew at that time, so they were good models. So now they need to be revamped, essentially. Any other questions?
The models don't last, like,
Not a little bit, but like a meter deep of in 150 kilometers, like, so that's a lot.
They allow for puddles, but you found lakes.
Yeah, essentially they allow for puddles, but not like huge lakes. We've found 3 of them so far. So, why it's in that specific region, we don't know. Why is it by the Huygens mining site? We don't know. Like, that's why we're still trying to figure this out. So it's essentially, so one thing that we're hopefully going to be doing with the surface albedo thing is seeing if there's any other lakes that they haven't discovered yet. And so this discovery of this lake was what prompted all the surface albedo studies after.
But there were other regions that absorb all the length and you guys look nice and looking at
Right. Right. So that's exactly what we observed for the north and south lake. But yeah, so it's the same characteristics that we observed for the south. Any other comments?